In this lesson, you will learn the basics of algorithm analysis. In this particular case, it's a time complexity with the big O notation, usually mentioned like this, big O notation. And it's really important that you get this right from the beginning, because like you saw in the code examples, when we were implementing the linked list, you saw that in the example of the dictionary, the program, loading all the data to memory was very slow. So if it's really slow on today's machines, imagine how it would be in the 70s, for example. It would be quite impractical, or in the 50s, it would be very impractical to use this kind of algorithm. So it's important to analyze why is it so slow even on today's computers. And this is where this algorithm analysis with this big O notation comes into play. And it's very important to keep this in the back of your mind, because you'll start being more critic regarding the algorithms that you choose and which data structures you choose for different problems. So let's see why our code was so slow. So if you remember correctly, we were loading a file to memory, which after we executed it, we saw that it has around 500,000 words. So our algorithm works perfectly fine when we had our contact list with just, let's say, 10 elements. But once the input grows a lot, to 500,000, and then it becomes quite slow. So imagine how it would be with the billions of users, for example. Let's use Facebook as an example, right? So it would be painfully slow, and let's analyze why that happens. In our case with the linked list, our linked list, every time that we read a word, I will use numbers for the sake of space. 1, here we have number 3, number 2, and now we have here a lot of others, and we continue with this pattern all over. The problem here is every time that you want to append, you have to traverse all the list until the end, find the last element, and put here another one. And even though this is very fast, as you can see, it's quite slow. So once the input starts growing a lot, you really feel that the algorithm is very slow. So what would be the time complexity of this append algorithm? So in the worst case scenario, usually when you talk about the big O notation, you talk about the worst case scenario. The worst case scenario on this case, which is not the worst case, it's like the constant case scenario, because it's always like this. So we always want to add to the end. We have to traverse all these n elements here. And the more elements we have, the more we have to traverse, which means that this is linear with the increase of the input. So the more input you have, it linearly increases. So let's say if it takes 1 second to add one element, then it would take 2 seconds to add 2 elements, etc. So mathematically, this would be a function like this that you probably learned in school back in the day, which is a linear function. So it grows like this. And if this function has what's called a time complexity O of n, so this would be a linear function, and we are repeating these n times, then we are multiplying by n this algorithm that it behaves as O of n. So adding to the end is O of n, but if we repeat this n times because we have n words inside in our input, then the completion of loading everything to memory is the repetition, n times repetition of adding all the elements. So this would be n times n, which is n squared. So this would be written as O(n) squared, and this would have a completely different representation. If you remember from back in the day in mathematics, this would be a parabolic function. And this is very, very slow. It doesn't matter what kind of machine you have. You might have a very powerful machine. If your algorithm is O(n) squared, it will be very slow once the input grows big enough. And as you saw from the example, it was very slow to load just 500,000 words. So how can we solve this problem? Try to think how this can be solved, and let's look at the solution in the next lesson. So see you in the next one.